You probably clicked on this video looking for help with how to use the Pythagorean theorem, and we'll get there. And you could even use the chapters in the video to skip right to where we do an example of this. But I'd like to start out with what actually is the Pythagorean theorem? Why does it work? What does it actually mean? Let's try to actually understand this math. Okay, let's take a look at this problem, this situation. It says both figures shown here are squares with a side length of a plus b. Notice that the first figure is divided into two squares and two rectangles. The second figure is divided into a square and four right triangles with legs of lengths a and b. Let's call the hypotenuse of these triangles C. Now we used a little vocabulary here that I want to make sure that you actually understand. So let's do a quick review real quick on what hypotenuse and legs mean. So the hypotenuse is the side of a right triangle that is opposite from the right angle. So you'll notice that two sides create the right angle. Those are called the legs. And the other side of the right triangle that's opposite from the right angle is called the hypotenuse, which will happen to be the longest side in a right triangle. But the easiest way to identify it isn't looking for which one's the longest, it's looking for which one isn't one of the two legs. And remember, the legs are the two sides that actually create the right triangle. Here's some examples of what that looks like. So now that we're clear on the vocabulary, let's return to this problem. Okay, so again, we're noticing things about the sides here. And we've defined what C is, so maybe we should actually label that in this problem. So let's throw in a C wherever we should have one. It's the hypotenuse of the right triangles with the lengths A and B. Okay, I want you to look around here and notice things about the areas. I'd actually recommend that you pause the video right now. You draw these diagrams and you try to find the area of each piece and then think about how the areas relate to each other. I'll give you a minute to pause and do that. Well, all right, let's take a look. What have we noticed? Let's find the area of each piece. So for example, the area of this would be a squared. Now think to yourself for a second, why is the area of that a squared? Well, the area of a rectangle is the length and width multiplied together. In this case, that's a times a. A squared means a times a, right? So that area would be a squared. What would be the area of this? Well, what's b times b? B times b would be, well, b squared. So the area of that piece is b squared. Well, what's the area of these other pieces? Well, they're a times b, right? ab. This one would also be a times b. Okay. Now, what would actually be the area of the entire large shape? So what if we wanted to know the area of this entire shape? What would that be? Well, it's a rectangle. So you'd multiply the side lengths together. Well, what are the side lengths? Aren't the side lengths a plus b, the length of a plus the length of b? So would you agree that the area of this shape would actually be a plus b times a plus b? Which, if you wanted to, you could write as a plus b squared. Okay, so we've examined and explored the situation in the first thing. That's the big thing about doing math. It's playing around, it's noticing things, trying to find connections and patterns. You don't always have an idea of exactly where you're going with it at the beginning. It's exploring. It's not just following a sequence of steps. All right, let's take a look at rectangle G. By the way, I've labeled the first one rectangle F and the second one rectangle G. All right, let's take a look at rectangle G. So what are the areas of the different pieces here? Well, let's look at this interior square, the one that has side lengths of C. What is the area of that? Well, you'd multiply the dimensions, right? Wouldn't the area of this piece be C squared, C times C? Well, we have a whole bunch of identical right triangles. What would be the area of each of those right triangles? Well, how do you find the area of a triangle? Don't you do the base times the height and then divide it by 2? They're half of a rectangle. So this one, for example, would be a times b, but then cut in half, divided by 2, or multiplied by a half. You could think about it either way. It's half of a times b. This one would also be half of a times b. Aren't each of these half of a times b? Okay, well, we've found the area of each of these pieces. Now, what can we do with this? What else do you notice? Well, what's the area of this large shape? Is it the same as the area of rectangle F? Has the same side lengths, doesn't it? A plus b. So this one would also be a plus b squared. Okay, so these two rectangles have the same area, but you should be noticing that they're divided up differently. Okay? They're divided up differently. Now, I want you to think about this for a second. How does the area of one of these right triangles that I'm using my yellow highlighter on, how does that compare to the areas in the shapes on the left? Well, what if actually I put two of these together? If I put these two together, can you find a piece on the left-hand rectangle, on rectangle F, that would actually match up to that area? Take a look. You can pause the video. Well, if you're thinking that half of AB plus another half of AB would be one copy of AB, and you're matching it up with one of these rectangles, well, I think you'd be right. Doesn't that match up? Okay, well, do we have another matching piece? What if we also highlighted this in yellow? I'm not very good at coloring in the lines, guys. Sorry if I'm overlapping and it's triggering anybody's OCD. Coloring in the lines is not my specialty. Now, well, I highlighted more. We better highlight the same amount on the left-hand side. And isn't this going to be also equal to that? So these yellow areas that I've highlighted are equivalent, right? They're the same. And the overall large area that we have is equivalent, isn't it? Okay. Well, what's left over here? Is the white area that's left over in each shape equivalent? Meaning this a squared that we have here and this b squared that we have here, is that equivalent to c squared? Well, it should be, right? Because if the area of the entire shape on the left is a plus b squared, and the area of the entire shape on the right is also a plus b squared, it doesn't really matter that it's a plus b squared. It matters that they're both equal. And if you take the yellow area away, what are you left with, right? What are you left with when you leave off the yellow area? The white area in the left-hand triangle is a squared plus b squared, but that's equivalent to the area in the right-hand shape, which is c squared. In other words, a squared plus b squared is equivalent to c squared in this. Ooh, I just threw my pen. Hopefully it still works. All right, so in this situation, a squared plus b squared is now equivalent to c squared. Well, what does that mean? Well, what are a and b? In this case, a and b are the side lengths in a right triangle. I'm looking at them right here. You could think of them as the side lengths in a right triangle. And what is c? C is the hypotenuse in a right triangle. So it seems like in this situation, what we really have here is that the value of one of the legs squared added to the length of the other leg squared is equal to the length of the hypotenuse squared in this right triangle. And this is what the Pythagorean theorem is, and it is what it actually means. And if we had bothered to explain why this would work for any right triangle, then this would be a proof that would explain why this is true for any right triangle. The basic outline of why that would work is that, well, you could create these shapes using any right triangle. If you started with any right triangle with legs A and B, you could arrange it into these identical shapes. You could arrange it in this manner, and because it doesn't matter what right triangle you start with, this same argument works. There's nothing special about these. This could be accomplished using any right triangles. Then that's why this would work in all cases. So this is a roughly outlined proof of the Pythagorean theorem. So now, what do we actually do with this? What is the Pythagorean theorem for? And that might be why you originally came to this video, is you need to solve a problem using the Pythagorean theorem. Well, what this is it gives you a relationship between the three sides in a right triangle, which means that if you knew what any two of them are, you can use this formula to figure out the third, because you know that they'll always follow this relationship. Let's scroll down and do some examples. So in this, we got two examples here. So we want to find the unknown side lengths in these right triangles. So the idea here is to align it to our formula. Remember, our formula is that the leg squared plus the leg squared is equal to the hypotenuse squared, although you're more likely to have learned this or memorized it as a squared plus b squared equals c squared. I like writing it down using the actual vocabulary because some people make mistakes on these. Some people make mistakes on these by putting the wrong value in the wrong spot, right? So I think it's valuable to memorize it and learn it using this method. Now, that means that we can just now lay out the values from this problem into the correct situations. So let's identify the legs. The legs, remember, are the two sides that create the 90-degree angle. Here's the two sides that create the 90-degree angle. So those are going to be our legs. And because the order of addition doesn't matter, it's commutative, you can fill in the 5 or the 2 in either of the leg spots. That doesn't really matter. So we could do this as 5 squared plus 2 squared. Or we could have done it as 2 squared plus 5 squared. Now we need that to be equal to the value of the hypotenuse squared. And the hypotenuse, let's use a different color just, to be colorful. The hypotenuse is over here, right? This is our hypotenuse. Remember, that's the one that isn't one of the legs, and it's across from the 90. So that would be x. And don't forget to put the square on it. It's squared. That's how the formula was developed, so that needs to be there. So now we've written down the values in this relationship. Now let's actually use it to figure out what x actually is. So let's simplify the problem. We could square the 5. 5 squared means 5 times 5, which is 25. We could square the 2. 2 times 2 is 4. And we could add those together. 25 plus 4 is actually 29. So this really means that 29 is equal to x squared. Well, that doesn't tell us what x is, does it? If x squared is 29, then what is x? Well, here's where you could use what's called an inverse operation. You can realize that if x squared is 29, then x should be whatever the square root of 29 is. Okay? That's what square root means. It means what number would you square to get, well, what number would you square to get 29? The square root of 29. So that's how you can solve this. The other way you can think about this algebraically is that you are performing a square root operation on both sides of the equation to undo or do the inverse of the square. That's another way you can think about that. All right, that's actually the answer right there. That's the answer. Although you might want to get a rounded answer, which would involve typing the square root of 29 in your calculator and then rounding it. I'm not going to get into that right now because you just type it in your calculator, and different calculators work different ways. All right, now let's look at the problem on the right. We're doing this one because these problems look a little bit differently if the side that you're solving for is the hypotenuse versus if it's one of the legs. The steps look slightly different, but you set it up the same way. Again, remember, we've got leg squared plus leg squared equals the hypotenuse squared. That's our relationship. Now we're going to insert the values into this particular problem. Remember that the legs are the two sides that create the 90-degree angle. So in this case, that's the square root of 8 and y. So we would have the square root of 8 squared plus the y squared is equal to the hypotenuse squared. Remember, the hypotenuse is the one that is across from the 90 and isn't one of the two legs. That's how you can always set these up in the correct order. All right, now we are going to once again simplify. Let's square the numbers that we can actually square. Well, what is the square root of 8 squared? This kind of seems like a trick question. It might seem complicated. You might want to get out a calculator, but actually think about this. What does this actually mean? The square root of 8 literally means the number that you square to get 8. So if you square the number that you square to get 8, you should get 8. Okay, so that seems more complicated than it is. That should just be 8. Now, what is y squared? Well, we don't know what y is. Y squared is just y times y. It's y squared. That one is not going to simplify. And then what is 4 squared? That just means 4 times 4, and that is 16. So we now have 8 plus y squared equals 16. Now, unlike our last problem, we can't just add some things together because I don't know what y is. I actually want to get y by itself, so I'm going to do some algebra here. I want to do the inverse operation, the opposite of adding 8. Let's do a minus 8. So if we do a minus 8 to this side of the equation, and we would also have to do a minus 8 to that side of the equation to make sure the two sides stay equal, they stay equivalent, then the 8 and the minus 8 would turn into 0 and just leave us with 0 plus y squared, which is just y squared. And 16 minus 8 could simplify to just being 8. So our sides now are y squared equals 8. Now, once again, how do we solve that? Well, if y squared is 8, then y must be the number that you square to get 8, which is the square root of 8. That's what the square root of 8 means. However, like I said before, you could think of this algebraically as doing the inverse operation of squaring, which would be square rooting. The square and the square root kind of cancel out. They undo each other, leaving you with y, and that's that. Okay? Now remember, you can type these in your calculator to get a rounded answer if you need to. All right, hopefully this was helpful for you. I should say that I have used some example problems here that I actually didn't make up myself. I've used them from an online curriculum I found that is published under the Creative Commons license. And that means I can use it for anything I want, including for my own profit. I can change it. I can do whatever I want with it as long as I give them attribution. Here's their Creative Commons license thing here, and I will also put that in the description to this video to make sure everything's good legally. All right, guys. I hope this was useful for you. If it was, hit the like button. That'll help me out on YouTube. You can also think about subscribing to the channel. That'll also help me out on YouTube, and it'll help you find more math help videos whenever I make them. I hope you have an excellent day. How do I end the recording? There we go.